Okay, we should be live. Thanks very much, Nomi. I will follow the chat just to make sure that someone eventually confirms that we are live, but let me skip my opening remarks and let Charlie take it away from the top. We can't hear you yet, Charlie, or I can't hear you yet. Jonathan, could you try speaking?
Yes, so should I start with my presentation then, or?
Is that okay, Charlie? I'll take that as a yes. Well, hopefully your audio will get resolved within 15. Jonathan, if you could go ahead and give us an introduction to RCPP modules.
Yeah, okay, no problem. So I'm very glad that we figured out those technical difficulties, and I try to keep my presentation in time. So let me quickly share my screen. So there it is. So you should be able to see it now, and the presentation is also online. So if you want to follow, just click the link in the chat. So I'm going to talk about RCPP modules, and I think it's a really nice feature of RCPP that many people don't know, and I myself discovered this really late, and I'm kind of sad because of this fact, because I think it's quite useful and awesome. So quick outline, we are talking about R and C++ classes, what they are, why they are useful. Then we are talking about RCPP modules, what they are, how to write them. And then, although we only have 15 minutes, I want to go through a from scratch example with you, a really small example, I think 50 lines of code or so. And then discuss what could be interesting for you to learn next if you find this talk really interesting. So let's start with classes in R. So in R, classes are kind of special because you have those S3, S4, and reference classes, and most of you probably know those S3 classes. So consider the code on the right side. You have this vector x, and then if you call class on x, it returns you the class, and in this case, it's just integer from 1 to 10. And then if you call some functions on this class, like sum or mean, those recognize the respective class of the object and then dispatch the appropriate method for this class. And this also works with more complex objects like models from LM-FIT or other objects. You can always call plot or summarize or that stuff. So those methods are like functions for a specific class, and for plot there is plot.lm, which is for linear models, and plot.ts for time series data, and so on. But this talk is really about classes in C++, and they are a little bit different syntactically from R. And I want to give you a brief introduction to those and what they do. So we have a formal definition from Wikipedia here. A class is a user-defined type or data structure declared with the keyword class that has data and functions as its members whose access is governed by the 3 access specifiers: private, protected, or public. And we are going to focus on public here because it's the simplest one, I would say. But the main part of classes is that you have data and functions in the same structure. So you bundle data and functions together. So essentially, those functions that are in your class share one common database, say. So one common set of variables that they have access to. And those member variables can be private, and then only functions of the class can access those variables, or they can be public, and then also other functions that use instances of this class can access those variables. So you can think of them as internal variables and like publicly exposed variables. So let's have a quick look at the right side. We have this student class here. So we define a class by writing down the class keyword and then give the class a name. And then inside of this class, we can define some variables. In my case, I want those variables to be public. And I create 3 variables for this student class: a string called name, an integer called age, and a bool called male. And then we define some functions for this class. So a class always has a constructor, and this constructor is called when an instance of this class is created. And the constructor is quite special because it has no return value. So if you are familiar with C++, you would expect that here at this point is some type keyword, and you don't have a type keyword because the constructor does not return anything. It's just called on in initialization of this class. And then you have an arbitrary number of different other functions, which are also called methods for this class. And some people like to define some getters, which just give you the variables that are inside this class. So this getName method would just return the name variable that we defined here, and this getAge would return the age variable, and so on. And then you can define more complex methods, which we will have a look into in 2 minutes. And we will define this allowed to drink function, which determines if you are allowed to drink, or your student which you created. Okay. So what's nice about classes is that you can bundle data and code together. So this is the most single awesome thing here, because when you don't have this functionality, you can either write a really, really big C++ function and expose that to R, which contains all the functionality you want to have, or you write little C++ functions and then have a lot of function calls from R to C++, and you also need to always return the data to R and then from R to C++ back. And sometimes those output objects can be really messy if they are quite complex. And another nice advantage of using classes in C++ is debugging, since you have access to those variables, and access to variables, to C++ variables from R is really beneficial when you are debugging and you want to quickly check what values are in a specific matrix or something. Okay, so you can write modular code with those classes, and it's more readable and you have more control over it from the R side. So let's talk about how to use C++ classes with R. And now RCPP comes into play, which is like a bridge from R to C++. And this has two features. One is called attributes, and most of the people who are getting started with RCPP think about this attributes feature. And attributes lets you expose C++ functions to R, but only functions. And modules lets you expose C++ functions and classes to R. And we are going to focus here on modules. And it's possible to use both features together. And I have a GitHub repository here, which you can click on and check out how this can be done. So exposing a function using attributes is pretty simple. You write this function in C++ and specify this RCPP export keyword or specifier, and then RCPP will know when compiling that this function should be exported to R. Exposing a module is a little bit more complicated, but it's also quite straightforward. So you give your module a name, which can be arbitrary, and then specify which class you want to export to R. And then you decide which methods you want to export. So you probably want to export a constructor, which has input arguments. So in my case, the student class has this constructor which needs a string, an integer, and a bool. And then you can expose as many methods or variables as you want. And we want to expose this getName method, and we want to expose this name variable as a field. And this is actually really neat because it gives us read and write access to this name variable. And we will also want to export this allow to drink method to R. And then if you compile this together with your class definition, you are basically able to interact with this class from R. Okay, so let's look at a complete example. So I took this from GORM Analysis, which has a really nice tutorial on RCPP modules on its blog. And there is a tutorial, a repository that I linked which contains an R package which only contains this class. So if you want to learn how to correctly structure the C++ code and put it into a package, just check out this repository. But it also works if you only have one standalone C++ file and compile it using this source-cpp function. Okay, let's quickly look at this, this example. So we include rcpp.h because we need this header, and we include string because we want to use a string type here for our class. Then we have this class definition that you already know from the last slide, but this is only a definition, right? So the implementation of those member functions still has to be done in a different place. So for example, this getter function here called getName is declared here, but it's not defined yet. So we have to define this constructor, those getters, and this method. Okay, so this constructor is relatively straightforward. We say, well, we want to define this constructor, which is called student. So the constructor always has the same name as the class, and it belongs to the student class, has those input arguments, and then we can write the values of those inputs into the variables belonging to the class with this syntax. And then you define your methods, like the getName method, which just returns the name. And you don't have to specify any inputs here because all of those methods can automatically access the member variables of the class. So this function automatically knows name, and this function automatically knows age, and so on. And then we define this allowed to drink function. It takes one integer called boundary, checks if the age in this class is higher than boundary, and then returns the answer as a bool. Okay, and if we want to export this class as a module, we can do this with this code that I already showed you earlier. We export our getter methods here, our variables as fields, and our method allowed to drink. Okay, and now quickly to the R side, we load RCPP. We call source CPP and source this C++ file, which we had earlier, and then we can initiate or create a new instance of this class by just calling new. So we want a new object of the student class, and we give those inputs to the constructor. So we want to create an instance of the student class with name Jonathan, age 15, and male is true. We can call structure on this to get a little bit on info about the structure. We can call allowed to drink here, and we get false because I wrote age is 15 here, and and I want to check if I'm allowed to drink, if drinking is allowed at age of 18, and it gives me false. But the awesome thing is that we get write access to those C++ variables. So we can just correct the age here from Jonathan, write 29, and now call the allowed to drink again, which returns true. Okay, so I'm out of time. Maybe you have some interesting questions for me. Check out my presentation if you want to dig deeper into this topic. Thank you.
Thank you, Jonathan. We do have one question for you from Robert Mueller. Can you also use class features like inheritance and others?
Yes, so inheritance is a little bit tricky here because at the moment, as far as I know, it's only possible to export, like one class. So we would have to try out if a subclass can be exported to C++. But what you can use is like overloading. So if you want to create different constructors, and basically one constructor takes a string as an input, and the other one takes an integer as an input, and you export both to R, then the dispatch will depend on which input you provide. So overloading will work, but I'm not sure about inheritance.
We may follow up with more questions as we go, but in the interest of time, thanks again, Jonathan. Let's see if Charlie is ready to go.
Great. Let me just share my screen. Is that good? Oops.
Yes, I'm seeing it.
Shall I start? Yeah, great. Okay, great. Thanks, Corey. So my talk today is on R's C interface. I'm a research scientist at Hibiki AI, and earlier this year we developed an R binding for a C library, and we proceeded to release that as an open source project. The C library that we wrapped was NNG, and that is essentially a socket library used for message passing and concurrency. And for those of you who might have heard of ZeroMQ, it is essentially a rewrite of that library in the C language, and it's designed for high performance. Why did we develop this binding? Well, as part of our machine learning workflows, we would often need to send data to another process for computation and then receive the results back. At the time, we were also using a Python-based machine learning framework. And so we needed a method essentially to bridge the two code bases. I'm happy to report that we are now doing that all entirely within R these days. Over time, we have added additional functionality to the package so that we are now actually using this to make REST API queries and also to receive live data feeds over WebSockets. So jumping straight to the appendices, of which there are 5. Because I'm only allotted 15 minutes for this talk, I cannot go into any of the code in detail, but they are there in the appendices of this presentation, the link of which I will provide at the end. There's a lot of good boilerplate stuff in there, that code that you can copy and adapt and use in your own packages if you so wish. This is a random playful graphic to just bring us back out of the appendices. So the question, why C? And the answer is C provides the ultimate performance. And why do I feel justified in asserting that? Let me give you one example, and this is from one of the first packages that I developed. And as part of that package, I needed to convert matrices to data frames, essentially to plot using ggplot2, for those of you who know. And the methods from the slowest as.data.frame you would probably expect to be quite slow. There's an RCPP method that you can use that essentially coerces a matrix to data frame. It's a very elegant 2-line solution. Even faster than that is a method that you can use that is written entirely in R code, but it's a bit more involved. And fastest of all is obviously doing a straight memcpy in C, where you're just copying from one buffer to another. So the thing to note here that it's not just simply that compiled code is always faster than interpreted code. In particular, note that the efficient method in R is actually faster than the CPP method, although admittedly that's probably not the fastest possible way you can do it in C++. Just to give you a second example, again for that package, it had to do some windowed operations. So these are calculations that are similar to calculating a moving average. At the time, I had implemented an efficient algorithm in C++. So this was a one-pass algorithm, and it used C++ standard library structures, double-ended queue and a pair to achieve that. And at the time, I was looking to see if I could implement that algorithm in C. So I started off with just using a naive algorithm, and this is essentially just one loop inside of another loop. And that is basically as far as I got, because that turned out to be faster than the so-called efficient implementation in C++. The conclusion here, I think, is that you do need to consider the hidden overhead in your code. In this example, it probably lies in the use of the standard library structures, but it could also be in the C++ wrapper. But suffice to say that the actual machine code that's produced from compiling your C++ may look very different to the machine code that you get from compiling C code. So back to the main topic of my talk, wrapping a C library. There's just a few topics that I wanted to touch on and discuss today. The first one is how to go about writing an idiomatic R interface for your C library. And by that, I just mean something that is easy to use and familiar to your R users. So to start going from C to R code, a lot can get lost in translation. One of the challenges is that C is not object-oriented, so often you'll have a lot of duplicated functions for different object types. Taking NNG as an example, the functions for setting options on objects. You'll have an ng socket set, context set, dialer set, listen set, etc. And I wouldn't suggest that you simply replicate those in R. What an R user might well expect is a function, for example, setup, that takes the object as the first argument, and then your options are set as a subsequent argument. Now, obviously, that can be implemented relatively easily as an S3 generic, but just to note that that isn't the only way you could do it. You could also do it on the C side. For example, you could wrap the object in a struct with a void member, and as part of that struct, you could have a type identifier. And I just want to say that the NanoNext package uses both of that for different situations. Second challenge you might face is that C functions are often too atomic. So the output of C functions may not map readily to R outputs. And what I want to stress here is that it is useless to try and wrap each C function. Technically, it might be possible, but it is just no way going to be anywhere near efficient. So what you would probably want to do instead is take your R inputs, pass them through a series of C functions, a mapping, if you will, and return some R outputs, which hopefully are actually useful values for you, rather than just some kind of intermediate state. And to give you a concrete example from NanoNext, this is the R function context, which creates a new context from a socket. The R code is a simple dot call down to the C function, taking a socket as the argument. The C code takes the socket, does some validation on the socket, it allocates memory for context, and then it calls an ng ctx open, which actually initiates the context. And then it creates an external pointer for the context, and then it sets a whole series of attributes. And at the end, the C code returns a context, which is a fully formed object back to R. So the considerations here is really how much of the work you do in R versus C. And that I think is entirely dependent on the purpose of your package. The premise is that each dot call is costly somewhat, so you wouldn't necessarily want to constantly switch between R and C, but you essentially have to decide to balance efficiency versus composability. And by composability, I simply mean the ability to reuse chunks of your code in different contexts. For NanoNext itself, performance was the key consideration, so hence many functions are called straight down to C code, and the R function is just a single dot call, as you saw on the previous example. Second topic I want to touch on is the external pointer, and this is really a powerful device when you have a C object that you want to keep around and reuse, such as a socket, which in the NNG world you send and receive messages over. The external pointer is an R object which keeps the C object alive. It's just a pointer to the memory address, and usually when you create the pointer, you also set a finalizer. So when the R object is garbage collected, it's just a bit of code that ensures that the C code exits gracefully and any allocated memory is freed. The third topic I want to touch on today is making a CRAN-ready package. And for us, that was one of the earliest considerations we had to make, whether we wanted to go and make a full-fledged package or not, because for it to be accepted on CRAN, it needs to be portable across the main platforms, which is Linux, Windows, Mac, and Solaris. There's likely to be some special treatment needed for Windows, which we'll touch on next, but for wrapping a library, you essentially have three options. One, you can rely on the system installation, and this you can refer to Jerome's anti-conf TM. This is a configure script that is found in a lot of the packages that he's developed. And essentially, the script just needs to detect different platforms, check for library versions, etc. The second option is to download and build the library from source. And this is, in fact, what NanoNext does at the moment, purely because we need a more recent version of the library than the versions that have made it into system repos. Your third option would be to bundle the source code of the library together with your package source code, and this is possibly more flexible and allows you to modify the source code if you so need, but at the cost of high maintenance, and then the upkeep of that code becomes your responsibility. So the special treatment for Windows that I mentioned just now, there are two tried and tested approaches. The first one is the WinLibs approach, and here you essentially pre-build static libraries and you need access to Windows bots to do that, or you could cross-compile. You host these libraries on GitHub or another public repo, and you include an R script, which traditionally has been named tools/winlibs.r, which downloads and processes those libraries as part of your package installation. The second option would be to attempt to actually build the libraries from source using Windows RTools 40 and now 42 toolchains. And this is supposedly the recommended approach, but just consider of the entire universe of Windows machines, those with the toolchain installed are likely to represent a very small proportion of those. But practically, end users are likely to rely on CRAN build binaries in any case, so practically either of those approaches I suggest will be fine. So this is the fourth and final topic I wanted to touch on, and I think this is possibly the most important point, is engaging with the community that you build. And by this I mean more than just making a package available and informing everyone of it. The key here is to contribute as much as you can, and what I mean by that is, at the minimum, I think being responsive to GitHub issues raised by your users. To give you an example, one of the first issues we got for NanoNext was from a user who was having trouble installing it on his Raspberry Pi. It was something that we were able to solve relatively easily, but it was quite exciting to learn of applications for your package that you might not have considered when you were building it. My second point would be to raise any suggestions or bug reports back to the upstream library maintainer. And this is, again, let me just give you another example. When we were building the async capability into NanoNext, this was quite a complicated process, and we ran into some issues that we solved ourselves, but it involved using mutexes and locking, and it was we were doing a lot of work that we felt was unnecessary. And luckily, the upstream library maintainer agreed with us, and so he actually implemented some changes to the library. And in our latest package version, we've actually incorporated those changes so that our package is now even more performant and robust as a result. So you can see that if you have a healthy community around your package, what you contribute hopefully comes back to you full circle and improvements in your own code. So I think this is a good place to leave the presentation. This is the link, which I'll also post in the comment box, where you can download this presentation together with the appendices. And for those of you wondering, this is Shikoku Chuo. Very nice time in Japan. Thank you.
Thanks very much, Charlie. I want to give it a few seconds in case somebody's in the middle of typing a question. And so I wonder if maybe you could give some very brief thoughts on the trade-offs or just preferences people might have between the native C interface and RCPP, which we just heard a little bit about from Jonathan. And I would open that to Jonathan as well.
Well, I can certainly sort of make a start. I mean, I think from our presentation, you probably know where I'm going to be coming from, but from a pure performance perspective, I think there's nothing that can beat the native performance, the performance of the native interface. But I sort of do caveat that in, and I don't think I'm necessarily qualified to do a comparison with C++ because I'm not a C++ expert myself, but just from developing various packages, I think C is very good for manipulating simple data structures. So if you have a matrix or a data frame or something like that, it's quite easy for you to construct those objects using C code. But if you're doing anything more involved, you're doing something fairly complicated with your data, manipulating data, it's probably going to be more efficient just doing that in R, because otherwise you're just rewriting R from scratch using C, and it's not even likely to be performant.
We don't have any questions in the Q&A, so again, in the interest of time, since we lost about 10 minutes at the outset, I'd like to go ahead to introduce David Dahl, and if we have time at the end, we might come back and discuss open-endedly. So David will introduce us to writing R extensions in Rust.
All right, can you hear me? Can you hear me?
Yes.
Okay, great, thank you. Hey, so I'm super excited to talk about how you can write R packages, R extensions in Rust. Now, Rust is a language that is something I'm really excited about. It reminds me of the children's book, Green Eggs and Ham, where there's a skeptical person who's trying to avoid having to eat these green eggs and ham that his friend is encouraging him to try. And I hope at the end, maybe you're willing to try something new, because I've been really happy with Rust. So, typically R packages are commonly R packages are commonly developed using C or Fortran or C++ for the sake of speed. We saw talk about C++, we saw talk about C. There is a document called Writing R Extensions maintained by the R core team that describes how to write R packages, including how to write R packages that interface with C and Fortran and C++. And what I'm trying to do then is provide then a guide for how you can write R extensions or R packages in Rust. And we have a paper that is under review that you could read that really captures all the details of the highlights that I'll be giving here in the talk today. What we have is we have something we call the cargo package on CRAN, which facilitates writing R packages in Rust. It addresses some of the idiosyncrasies of R and Rust in any integration that one would have, and also avoids some pitfalls that might prevent your package from being accepted on CRAN. And then finally, the cargo package also allows you to embed directly in your R script Rust code. Okay. So let's give some background on Rust. It's a statically typed general purpose programming language, and it emphasizes performance. So it does reach performance of C and C++. It's very close to the metal, very performant, yet it's also very reliable in the sense that it has some memory safety guarantees such that you're free from typical traps of memory leaks or using a memory after it's been freed or whatnot. And it converts many memory errors that you would otherwise get in C or C++ to compile time errors that you can then solve before you actually get into runtime, where it's harder to address those issues. Also, it's very productive. It's a new modern language with a lot of really helpful tools involved. It avoids garbage collection altogether. but yet, again, you don't have to explicitly think about freeing memory because of the model that it has, and the compiler's very strict borrow checker, which you can think about the compiler as being a very, very stern and strict, but yet helpful friend. And oftentimes I'll have a mistake, and the compiler will suggest what I need to do to fix the mistake, which is just a breath of fresh air. Also, you can very easily do concurrent programming in Rust, and you can do so fearlessly because the memory borrow checker will ensure that you're not accessing the same memory at the same time and whatnot, all in compile time checks, which converts then concurrency errors to compile time errors, as opposed to difficult to reproduce runtime errors. So Rust has been rated since 2016 every year as the most loved programming language, according to the Stack Overflow Annual Developer Survey, where this year we have Rust at the top, as we have since 2016, but it's right up there with other languages that are very well liked, such as Julia and Python, and far above, say, Java or C++ in terms of developer experience. There's also the Rust Foundation, which started last year, supported by all the big tech companies. You can also develop now Android applications using Rust. Here's the new documentation from Google about doing that. And you can also experimentally develop drivers and subsystems in Linux using Rust. So there's a lot of interest in Rust in the developer community. And in fact, there's also been interest in using Rust in R. And Jeroen Ooms, I believe I pronounced his name correctly, was the first to have a package on CRAN that used Rust called GIFSKI package, but also gave a really nice presentation in the 2018 European R users meeting that describes how you can integrate then R and Rust. Now, his integration requires you to write C code, which then calls the Rust code. And the Rust code itself doesn't have access to R's API. Now, I followed that for my package called Salsa, which was then the second package on CRAN that used Rust. And then another one, Baseflow by another author. But then in 2020, CRAN maintainers noted that we violated, all three of these violated some CRAN policies and needed to make some changes. So that inspired me in 2021 to write my cargo package to facilitate CRAN compliance and to avoid the need to write the C glue code. So therefore, R and Rust can now call each other directly using my package. Now, I would be completely remiss if I didn't mention another really exciting project called Extendr. And this Extendr package has a similar goal in the sense that it's trying to integrate R and Rust. They're actually more ambitious than I am. They're trying to, for example, allow you to not only develop R packages with Rust, but also to allow you to embed the R interpreter in a Rust program. The Extendr and the cargo packages are different in how they address several technical issues, and they have some different design trade-offs. And so I would say that the R Extendr approach has many high-level conveniences and many behind-the-scenes type conversions for you. But it's still definitely a work in progress, such that they're still working on some of the conventions they'll do. Whereas my cargo package, I would argue, is a little more transparent in the sense that you have all of the Rust code in your R package, and you can see directly exactly what it's doing, and you can modify it as you need. And the API is perhaps more stable. Okay, so enough talk. Let's show how this would work. Let's jump over to RStudio. And you can install with install.packages cargo, and that'll pull it down from CRAN. I've already done that on my machine. And then you can install the Rust toolchain, the Rust compiler, by saying cargo : install. And it will ask you, hey, can I go off of the internet and install Rust in this specified location using the standard Rust installer? And there you go. Once you've done that, in RStudio, you can go over to File, select New Project, and select New Directory, and scroll down to Cargo Framework, Create R Package using Rust. we'll name our package demo. And then the first time, the compilation has to start from scratch. And so it's going to take about 5 or 10 seconds to do the compiling. We see we have to wait a little bit. And in just a minute, I'm going to have a new RStudio window pop up on my machine, which I'll pull over to the shared screen. There we go. And so now I'm developing my demo package. Type library demo. And I can, for example, call this function myRnorm, which is an example function that ships with the skeleton. And I'm going to generate then, say, 20 values from a normal distribution with mean 2 and standard deviation 10. And there we go. And so that is just using the .call functionality to call low-level code. Typically, this would be a C or C++ function, but in this case, it's a Rust function. Well, where do we get that Rust function? Here off to the right is my package skeleton. We have to drill down a little bit. And we get to the Rust function, myRnorm. And it takes these 3 input arguments, all of type rval, and returning a type rval. Now, for those of you familiar with the C API for R, you'll know that all of the functions that you call from R into C always take of type SEXP or an S expression pointer. And the rval is like the equivalent of that in Rust here. And I'm importing the Rust bindings, the R bindings. And so now I have access to all of these C functions that R provides that allows us to, for example, allocate a vector and protect what we just allocated, to get the random number state and to put it back, and to unprotect, all those things. Now, suppose I wanted to make, say, a new function. Okay. Let's make a new function called myRstd norm. I'm going to make a standard normal. And we're just going to draw from standard normal, only take 1 argument. Okay. Should be good there. And now I need to go back over to here. Now I've got a new function. How do I get the R function linked up with the Rust function? What I need to do is to say cargo pre-build. And now I'll recompile the package. And now I can call my rnorm. And now I've got draws from standard normal. So really easy to connect R and Rust through this interface. Now you might say, well, wait a second though, that's fine, but like I'm a Rust developer, I don't want to be using a C interface, RC interface. All these functions here feel very C-like, which is fine. And so we also have a high-level interface, which I'll show you now. So in the Writing R extensions, there is an example, convolve2, which shows how to convolve 2 vectors. And they give you some nice code that does that. That's exactly the same code that I have here, where we're calling coerce vector and protect, and we called protect 3 times, so to unprotect 3 times, etc. Well, here's the equivalent high-level Rust code that does the same thing, where we have the 2 arguments, and we convert them to doubles. And we then end up getting the coerce new potential R value, but we also get a smart pointer into the memory of that R value. And we could then use that to do the computation and make the return. One noticeable difference is that, well, this feels very Rust-like in the code, but also we're not having to worry about counting the number of protect calls and then unprotecting by the same amount, because we have a protection counter here that will automatically protect items that need to be protected, and will automatically unprotect by the right number because of some nice facilities that Rust provides. By the way, we have some nice API documentation. So here we have the low-level C functions that R provides, all of them. But we also have then our high-level interface that allows us to, for example, create new vectors that are doubles or integers, to check if something is missing, to make matrices, to assign values, to set attributes, etc. All right. So I also mentioned that you can embed Rust code directly in an R script. And that can be convenient if you've got a short little computation you want to do, but you want to do it very quickly. In my case, I needed to work on a problem where I needed to solve something called the linear assignment problem. And it's something for which there was an R package, but it was actually quite slow, despite the fact that it was written in C++. It was just a particular implementation of the algorithm wasn't terribly fast. And so I found another implementation that solved the linear assignment problem in Rust, available in Crates.io. Now, Crates.io is like the equivalent of CRAN, where they host what are called crates or packages for Rust. And it's very easy to publish a package to Crates.io. The first time I published a package, I decided to do it, and it took me 15 minutes to actually get it up there. And now when I want to resubmit, I can do it in a matter of a second or a few seconds, one-line command. There's no human intervention in that. So really, the quality of a package on Crates.io is determined then by the number of people that are using it. We can also use this fact that we can embed R functions in our Rust functions in our script to actually do some benchmarking. So consider computing the Euclidean norm of a vector. Here's some cargo code or Rust code that would compute that in a very natural Rust kind of way. Here's some C code that does that same computation. And the question is well, how fast does Rust and C? These are very short-lived functions. Let's see how quickly we can jump in and back out. We also used rextendr with a couple of different options where they do some automatic conversions or not of some types, and they do some caching or not do some caching to make it a fair comparison. And we find that our performance is very close to that of C, but yet the performance of rextendr is not as strong. So we're really excited about that. We have to do a little bit more overhead than C does to, for example, handle gracefully panics in R, or to avoid long jumps in R. But anyway, our package does provide those facilities to handle the idiosyncrasies associated with R and Rust. And again, if you're interested in the paper, please look it up, writing R extensions in Rust. Lastly, I'll say that following our framework allows you to make Rust-based packages that are likely to be accepted by CRAN, in the sense that we run cargo with only 2 threads, and we make sure that there's no residue files left over, cache files left over, even though cargo tends to want to have cache files. We also allow you to build your package, even if the Rust toolchain is not installed on the CRAN server, and allow the user to satisfy the dependency for having the Rust compiler. So anyway, we're really excited about Rust, and I hope that if you're interested, you'll look it up and try it yourself. Thank you very much.
David, thanks very much to you too. I wonder if you'd be able to stay a little bit after time in case we run out. There are a couple of questions which I'd love to get to, but I don't want to leave our final speaker bleeding over the end of the time frame.
Great.
Thanks very much. Edwin, if you'd like to go ahead and tell us about RV, recreational V programming.
Sure. Well, thanks for being part of this very interesting presentation or session. I'm trying to share my screen right now. And so I have to open my presentation. the screen. Oh, I'm not seeing it. Share. Ah, there it is. So can you, everyone see my screen right now?
Yes.
Oh, thanks. Well, I'm going to talk about V and R for RV. So recreational V programming for R. And R plus V is RV. So first of all, where am I? I'm Edwin de Jong. I'm statistical consultant in R&D at Statistics Netherlands, or the official Bureau of Statistics in the Netherlands. I'm author of some R packages, including Whisker and .doc and several others. I really love R programming and I like programming in general. So RV is just a hobby project. V is a young and simple programming language. It's really a nice programming language. It's really not very well known. So the short summary of this presentation is that RV helps to create R extensions written in the V programming language. RV generates from V all wrapping code and implementation code in C, and in the resulting code there are no runtime or other R dependencies than the generated C code. So what is V? Well, V is a programming language with an own website, of course. The website is vlang.io. It says about itself that it's a simple, safe, compiled for developing maintainable software. It's a young language, it's low level but simple, and it feels a bit like scripting, but it's strongly typed and compiled. And the website itself boasts itself that the language can be learned within a weekend, well, according to the website. It has lots of features for such a young language, but that's quite nice. For example, it includes a REPL, so you can type in statements and these will be compiled on the fly. The syntax is very similar to Go, but it improves on Go. So there's a whole section on what it does different from Go. It's very lightweight, and of course, it's a one-letter language. Okay, I know that's not a non-argument, but C, R, and V are all, well, nice one-letter languages. So this is just an example of the syntax. So this is a function definition. It's really a bit C-like, but it really resembles Go. And it is a strongly typed language, but you don't have to specify types if you need to. V is also a very safe language, so there's no null or undefined values, because according to many modern languages, null values or unexpected null values causes lots of software problems. So functions returning null values or non-values when they are supposed to give return values are causing all kinds of trouble. Rust has a different solution for that, but many other languages do cope with that. Immutable variables by default, so making it easy to optimize and reason about code. V, like Go, includes an option or result. So functions can return a question mark type, or for example, question mark int, and the compiler generates an error if an empty return is not handled properly. So when the return value of a function is prefixed with a question mark, the compiler knows that this function might return a null value or a non-value. There's also a result type, so function can result in exclamation mark type, for example, exclamation mark int, and then the compiler knows that there might be an error generated. So if a function returns a type, the function always returns that type, and the compiler checks for that. So that creates quite some safety. The other thing is that functions are pure by default. Purity And if you want to be impure, so change variables, you have to be explicit. Phi features easy C interop, so you can quite easily connect with C functions. It's cross-platform. They have a sort of structs with method dispatch, and the compilation is very fast. So this is just summarization of the website, zero cost extractions, sum types, includes generics, which is one improvement upon Go, although Go is getting generics too. Has this optional result thingy, and including an elegant way to handle with non-values or error situations. And there is explicit mutability of variables using the keyword mute. So the website itself says these are the self-compilations. So each programming language compiled with its own compiler. You can see that well, Phi is what Phi is doing is really impressive. So Phi is written in Phi itself, and it needs 10 megabytes to compile, and the build time for Phi is less than a second. These benchmarks are not mine, these are just from the website. So the performance of Phi is it's as fast as C, because Phi main backend compiles to human readable C. There's also a feature called built-in serialization. So it's a very nice JSON feature, so you can use structs to generate and read JSON files, for example. So these are hard compiled and compiles to native binaries without any dependencies. And they have a simple web server in about 65 kilobytes. Phi can also compile to other backends, just like any modern programming language nowadays. It's not as feature complete as Rust or Go, but it can compile to native code, readable C code, and JavaScript. And I think WebAssembly is planned or coming. So Phi has some similarities with R, superficial similarities, but nonetheless. So Phi functions are pure by default, which is a bit similar to R, because in R, most R functions are pure. They have no side effects. And R uses copy and modify, so the arguments are not immutable by default, but for the outside world they are. Phi has a simple syntax, is very flexible comparable to R. Phi has something called defer, just like Go. So you can, within a function block, you can call some code that will be executed when the function is exited, just like R's on exit. And you can write method that works on structs. So that smells a bit like S3. Also has some reflection of code generation, but R is way superior to reflection and syntax, building its own syntax. So Phi has some very flexible module and package system containing Phi source code. And this package system doesn't contain compiled code, but just Phi source code. So when you do a compilation and you use extra modules, this Phi code is included within the compilation, and it results in just one binary using executable or a library. Phi also includes a standard formatting tool, so all code can be formatted uniformly. And there are some other features like nice visual code integration. So what's RPhi? So RPhi is an experimental R package to create R package extensions with functions written in V. Well, it's a bit similar to RCP and also, I guess, to what I just saw, RExtender and Cargo, but way less mature. So it generates from the Phi source code C code, including wrapping code for all the creating all the libraries, and it can be used just as a C R package extension. So there are no compile time or runtime dependency in the resulting R package. And I wanted to use the name RV, but that was already used for another package for simulating random variables. And why am I doing this? Well, one of the nice things about R is that it is a glue language. Well, it's of course a physical language, but it's basically also a glue language on top of other languages, just like its precursor S, which was a kind of a glue language for Fortran and C code to do some statistics with these code. And Phi is a nice low-level language, so why not? And of course, this is fun to write extensions. If you look at RV, there could be two possible routes for using Phi as an extension for R. So you could use the Phi compiler to link to R, but that requires V to be present on while you're building the extension, for example, CRAN. The other route is to use the Phi transpiler to C and create a normal R package. And this is RV. So with RV, you can create C code, which is just C code for a normal C extension package. So RV transpiles this Phi code into C package code, including all wrappers. And it also includes a V package with V code that is wrapping the RC API, which is nowhere complete right now. It's about 30%, but all the main stuff is working. So factor and data frame functions are working, and you can build functions around that. So there are two functions right now in RV. One is RV underscore export underscore C. So what you have to do is put your Phi code, source code, in your source package directory. You can decorate each function in Phi function to be exported with this V attribute. So in your Phi source code, you can place before each function R underscore Phi of RV underscore export, and then calling the RV export C function, it generates all the wrapper functions. So it generates an R script with the R functions calling the V function decorated in the RV export Phi R wrapper functions, translating R constructs, or the S expression objects, into V expression into V code, to the original V functions. It generates the registration code, which is used for the shared library, and it generates C code, which is the translated original V code. So that's 1, 2, 3, 4 files, and you can include these in your package, and then you have just a normal R extension package, and no dependencies whatsoever. If you have done this, then DevTools or R command shared library should work on the generated C files. The other one is Phi underscore function, and this is quite similar to CPP function, and if I remember correctly, the the Rust underscore fn function. So you can use Phi code. So this is a very simple function right now over here. So this says function add x, y, z, and the result should be an int. This is a declaration, so sum is also an int, and it's immutable. It's a constant or immutable. That's of x, y, and z, and it returns sum. So, and you can compile this one, and if you do this, it will use this name to add this to the R global environment, and it will contain an R function called add, which calls this V function. So in the RV package, there is also a wrapper library called R API, and it helps to transform V strings arrays into R vectors and vice versa. So what's the status of RV? So V itself is a young language, but it's already quite stable. It's of course, tiny in comparison to Rust or Go or C++, really tiny in community, I mean, but it's a nice language. Generated code is in C. RV itself is still experimental, so help is welcome. So experimental, so expect breaking changes, but it works. And if you generate C code with it, then you can do your thing. And of course, it's fun to write R extensions. So I would like to thank you for your interest. And if you're interested, just install the package and give me some feedback. Okay, are there any questions?
Thanks very much, Edwin. Any questions are welcome at this point.
I have a question for Edwin. Can you hear me?
Yeah, I can hear you.
So Edwin, that sounds really exciting. I'm interested to learn more about this. Question is, do you need to have the V compiler on the CRAN build machines, or can your package just ship the intermediate C code generated by the V compiler?
The last one. So yeah, so I use RV to generate C code, so the CRAN doesn't have to have the V compiler. Yeah.
Yeah, that's nice.
Yeah, yeah. Yeah, I think both ways are nice, but since it would take me more effort to get the V compiler on CRAN, I guess. Yeah. And Rust has enough body to. Or I'm not aware of the status of Rust right now. Is Rust available on CRAN?
So it has been, but not actively updated. And so that's one of the things I had to work around is
yes.
My package actually ships some Rust code in the binary, and then the user themselves can provide the Rust compiler.
Yeah,
it's
yeah,
a bit of a hack.
Yeah, I know, but you have to do well. It's a smart hack, I think. Yeah, yeah.
And we do have a few more minutes if there are additional.
So Corey, did I hear your question or your?
No, sorry, I was just alerting attendees if there are additional questions now.
Okay.
We have a couple more minutes before we have to close the session. Well, I'm glad to stick around for a while. If anyone needs to go, then you're welcome to, of course. Thank you all, David, Edwin, Jonathan, and Charlie, for your wonderful presentations today.
So Edwin, what do you think needs to be done in V before it reaches what version 1.0 or something?
Oh, yeah, that's a difficult question. I don't know exactly. Well, it's quite stable, but the website itself or the main developer is really proud on. There are two different memory allocation methods within V. So there's a garbage collector method that works, but there's also an auto-free mechanism, and there are some that auto-free mechanism looks really nice, but it's not bug-free at the moment. So I think that's the main problem. And the other thing is the main developer is right now developing an OS in V called Vinix. And I think his main effort is going into that. So that's the other thing. Yeah. The language itself is quite nice. It's really easy. Yeah.
Charlie, with your interface to the C library, do you have any tricks or suggestions about how to keep that? It seems very brittle to the extent that the C library changes.
Yeah.
And not your fault at all, but that's just the nature, I think, of these bindings.
Yeah.
Do you have any advice for developers?
Well, that's a good one. Now, I
For me, or happy for you to answer, Edwin?
I would address it to Charlie, but I'm happy to hear Edwin's thoughts too.
yeah. Well, I'm still figuring that one out too. Yeah. So I'm happy to hear Charlie's thoughts on this.
Yeah, sure. I think on my side, the C library changes in frequency much slower even than the R ecosystem. For a start, the library is fairly mature. It's what you find in system repositories is already maybe 1 or 2 years old. The API is stable, so the C API practically won't change. The change that we ask the maintainer to implement essentially is just a new function. So anyone who was using the previous versions of our package and the library, everything will still work. It's likely to be incremental changes. So I don't think this is, in our world, I think a parallel might be tidyverse. I hear that sort of the interface changes quite frequently. I think from what I've seen, at least, especially the more established C libraries, the interface doesn't change or changes very, very slowly. So I don't think that's a concern, at least for me. But I think also you do have to choose which libraries you want to wrap in the first place. Because I think, as with anything, you don't necessarily get any quality guarantees, but with large, established, successful projects, then you have some assurance that the interface will be fairly stable.
In the same way that we were not sure how to begin the session, we don't seem to have the button to end it. So I believe Nicole is going to have to take care of that behind the scenes for us. So thank you all for attending, and let's wrap it here.
Great. Thanks, everybody.
I think.
Yeah, thank you very much. Bye.
Bye-bye.